we'll start talking about submodules next. So what's a submodule? So here's the definition. So if R is a ring and M is a module and M left R module. So again, as I said a few times already, we will usually just suppress this word left, and when we say just R module, we usually mean left R module. So suppose I have an R module, then definition, a submodule of M, a submodule N of M, well, it satisfies two conditions. Firstly, is a subgroup under the addition operation, subgroup under addition, okay, and which satisfies the following property, that it's closed under scalar multiplication. Okay, it satisfies the following property: alpha dot n belongs to n for all alpha in the ring R and for all elements n in the set n. Okay, in other words, the set n is closed under addition and scalar multiplication. So that's what a submodule is. Okay, it's a natural definition. The obvious examples: if R is a field K, in this case recall that R modules are just the same as vector spaces over the field K, and of course it comes as no surprise that submodules are just the same as subspaces. So in this case recall submodules of M, recalling the definition of subspaces, are the same as subspaces. Vector subspaces of the vector space N. Okay, now there are some obvious submodules always. So given any module N, I can construct two obvious submodules: the 0 module and the entire module M. So these are sometimes called the two trivial submodules, the 0 on one end and M on the other end. Okay, and let's take another example. Recall that last time we spoke about a ring R. So if R is any ring, then R is a left module over itself by the left multiplication operation. Via the following action: alpha acting on X is just alpha X for all alpha in the ring R. So that's, I think of that as scalars, and X from the ring R again, that's the module. So this is the left multiplication action that makes R into a module over itself. And in this module, what are the submodules? So observe that if I take a subset of R is now a submodule for this particular way of making R into a module. It's a submodule means that well, by definition, that N is an additive subgroup, is a subgroup of the additive group of R, and further condition number 2 says that if I do alpha times n, now this is the usual multiplication in the ring, alpha n belongs to n for all alpha in R and for all n in n. Okay, now recall from the lectures on rings that this pair of conditions that we've just written out, these two guys, is exactly the definition of a left ideal. Okay, so in other words, submodules of the ring R under this left multiplication action are the same as left ideals of R. Okay, and I leave this as an exercise for you. You can also look at the right submodule. So let's just quickly define that notion as well. If R, or rather if M is a right module, then we can talk about submodules. Then submodules of M are so now we need to define this notion of a submodules. So let me just say N is now a submodule of N. Then we say N is a submodule of M if it's closed under addition, if N plus is an additive subgroup. Well, it's a subgroup of M plus is a subgroup and we have the closeness on the other side. N acted on the right by alpha belongs to N for all N in N and for all alpha in the ring R. Okay, so this is the right action, and observe that just like we did the earlier thing, we said if I take R thought of as a left module over itself, then left ideals and left submodules are the same. Similarly, if you think of R as a right module over itself, then the submodules turn out to be just right ideal. So if R is considered as a right module over itself, considered as a right R module, then submodules of R turn out to be submodules of R are the same as right ideals of R. Okay, by the same argument that we just gave. Okay, so these already give us plenty of examples. So if I think of R as a module over itself, so if you look back on the lectures on rings and left and right ideals in rings and so on, you can write down lots of examples. Excuse me. So for example, I can take make various choices of rings. For example, I can take the matrix rings M and K, and in fact the left and the right ideals of M and K were determined in one of the earlier lectures. So if you recall the notation there, the ideals look like this. I can take any subspace V of Kn, and you had R of V, which was the set of all matrices in M and K whose row space, which means the span of the rows, is contained in this fixed subspace V. And then there was C of V, which is similarly the set of matrices whose column space is contained in V. So let me just talk about the row space for the moment. I'm just looking at left ideal. So this is in fact a left ideal. So in other words, it's a submodule. Okay, so this I'm sort of recall from the previous lectures. Okay, so that gives you an example of a left submodule of a submodule of the ring of matrices acting upon itself on the left. Okay, and of course similarly, I mean, this was a non-commutative ring. You can look at commutative examples as well. So I could, for example, take any commutative ring. So of course you've seen many examples already. So look back on the examples of ideals in commutative rings. So now of course recall that left and right, there's no distinction anymore. Left ideals of R are really the same as what we call two-sided ideals or ideals. And of course, ideals were determined in many different examples before. Okay, so this is just to say that you already know lots of examples of submodules because you already know lots of examples of ideals in commutative rings or left ideals in non-commutative rings. Okay, so that's already many examples, but let's do a few more. So here are some more examples of submodules. So we number it 1 again. So if I take the ring to be the ring of integers, then M, recall Z module is the same as an abelian group. So N is any abelian group. Okay, so that's a Z module, and in this case it's easy to show, and I will leave that as an exercise, that N is a submodule. It's a submodule. So let me just put Z submodule of M, or maybe just say submodule. So we already said the ring is Z. This is a submodule of M is actually the same as saying it's a subgroup. There is no additional condition here. N plus is a subgroup of M plus. Okay, and the reason is not too hard to see. Recall that the Z module structure on an abelian group is more or less forced. Okay, you can't do much. You have to use the addition in the underlying addition to define the multiplication by scalars. Okay, and so in some sense the same sort of argument proves this statement as well, that submodules are just the same as subgroups. You just pick a subgroup, that's automatically a Z submodule. Okay, because multiplication by a number n is just repeated addition. So if it's closed under addition, it's automatically closed under repeated addition. Okay, so example 2, which is slightly less trivial, which is our ring of polynomials in a single variable. So let's take K to be a field and R to be the ring of polynomials. And now here recall from one of our earlier lectures that how do you construct modules over this ring Kx? The way you do it is, well, a module can be obtained by starting with this pair V comma T. So if I start with V, which is a K vector space, just in the usual sense of the word, and I need to start with a linear operator on V. So T from V to V is a linear operator, okay, or a linear transformation. So if I give you these two things, then it uniquely defines a module, a Kx module structure on V. Then recall V becomes a Kx module by the following prescription. So these two pieces of information, that V is a vector space and T is a linear operator, these two things define the actions of, so how does alpha act on V? This is just the usual scalar multiplication. So this is for all alpha coming from K and for all V in V. Okay, so when I say alpha, I think of it as the constant polynomial. Alpha is just alpha plus 0x plus 0x square, if you wish. I can just put zeros on all the other higher powers of x. So the constants, the constant polynomials alpha act on V by just scalar multiplication. So that's the first. And the special polynomial x power 1, the degree 1 polynomial, homogeneous polynomial x power 1 or x, the way x acts on V is given by T. Okay, so this is, you can think of these two as the two defining properties. And of course these two automatically tell you what a general polynomial does. If I take alpha 1x plus alpha n x power n acting on V, it is just alpha naught V plus alpha 1 t V plus alpha 2 t square V and so on. Okay, so that was, recall how we made V into a Kx module. Okay, now the question is, what are submodules now? Okay, so let's now ask, what are submodules of V now? Okay, so these are now Kx submodules. I'm thinking of V as a Kx module now. So what's the definition? So let's see, when do you say something is a submodule? So suppose n is a submodule, means that firstly it's closed under addition, n plus is a subgroup of V plus, and secondly it's closed under scalar multiplication. Okay, so it means if I take any polynomial Px from Kx and I act it on V, the answer is in n again for all V coming from n, and for all polynomials Px in my ring Kx. Okay, now what we'll do is in particular we'll apply this condition here, that Px V belongs to n. We'll apply it to those two special polynomials. Let's take constants and let's take x power 1. So in particular this implies, the second condition means, if I take a constant or if I take x, okay, take these two types of polynomials, I act it on V, the answer is again in n for all V in n, and this belongs to n for all V in n again, and this is also for all scalars alpha and k. Okay, so what do I conclude? The first condition, which says that if I take a vector from n and I multiply it by any scalar from k, the answer is again in k. Okay, so this property, together with the fact that, so recall also we know something more about n, we also know that n is closed under addition is a subgroup. Okay, so these two properties tell you exactly that n is a subspace. This is exactly what a vector subspace is. Okay, so these two properties, what I marked in green, say that n is a vector subspace of V. Okay, and now this additional property, let's see what that implies. TV, remember, is just, I'm sorry, xv, remember, is just TV. So this says that if I take an element of n and I add t on it, I get back an element of n. In other words, this says that the subspace n, if I add t on it, I get back, it maps n to n, vectors in n to vectors in n. So what does that mean? Well, these two properties are exactly the definition of what's called a T invariant subspace. So n is a T invariant subspace of V. Okay, and of course you can just reverse this entire chain of arguments and conclude that a submodule is the same as a T invariant subspace. So I can just put all my arrows back. Okay, and you have to check one last thing, that if TV is in n for all V, then in fact a more general polynomial, so remember this is our general polynomial acts, the action of a general polynomial on a vector from n will also give me a vector in n. Okay, but that's because if it's T invariant, then it's also T square invariant and T cubed invariant and so on. Okay, so I'll just leave this last bit of checking to you, and here's the final conclusion, that n, so let me just record the conclusion, that n is a submodule of V. It's the same as saying that n is a T invariant subspace of V. Okay, and this is the T here is, it comes from the way V has been made into a Kx module. X is acting by T. Okay, that's the T we are talking about. Okay, now so that's the second important example.